questions? Okay, so last time we talked about how to do the derivative for different operations. So we talked about this. And we talked about this. And we talked about this. And then we talked about one more. So what were these three, though? These rules were the easier of the rules. What were they? What's the first rule?
So,
What's the first rule? What goes in each place?
first, derivative of first.
The derivative of the first one plus the derivative of the second one. And plus or minus. Okay, is that clear? What's an example of this? An example would be if I asked the derivative of 5, well, there was actually one more before this. This one was what? So what's an example of this one?
2x.
The derivative of 10x to the third is equal to what? Using this rule, the top rule. 10 times, well, just one step at a time would be what? 10 times the derivative of x cubed, right? That's how you'd use that rule. Okay? And then what is the derivative of x cubed? 3x squared. So the answer would be 10 times 3x squared, right? Or 30x squared. Okay, is that clear? That's the first rule. Now, just before you get so caught up in these rules, what does derivative tell you again? For example, suppose we have this function, 10x cubed. Okay, first of all, what does that function look like?
Yeah.
So, maybe you know what it looks like. Maybe you know it looks something like this. Like something like that. So suppose it does look like that. So suppose this is 10x cubed. What does the derivative tell us anyway? What's the point of the derivative?
Tangent of the line.
What?
Tangent of the line.
Tangent line. Right. So what does it tell you? It tells you the slope
Slope
of the tangent line, right? So like if I said, okay, how about when x equals 1? When x equals 1, what's the height of this function? What's the y coordinate? 1 comma what? Y equals what? 10, right? So y is 10. Okay? But that's not the derivative. The derivative tells me what? Tells me the slope of what? Of the tangent line at that point. Where's the, so I can sketch the tangent line, like something like that. right? And the slope of that, now you say, well, I don't care about that, I don't want to know about the slope of that line. But that has another meaning, and that's called the instantaneous rate of change. So it's telling me how quickly it's increasing or decreasing, how quickly it's increasing. So, okay, but now, okay, so what is the derivative? We said the derivative is this, or in other words, it's 30x squared. So how do I find out the slope of this line? I put 1 into the derivative, not into the function. If I put 1 into the function, I find out what? The height of this point, right? But if I put 1 into the derivative, it tells me something else, hopefully, because I already know the height of the point. So I don't really want to find that out twice. But the derivative will tell me something else. What will it tell me? The slope of the tangent line, or in other words, the instantaneous rate of change at this point. Just before we check it though, which has a greater instantaneous rate of change? At this place or at this place? Which has a greater rate of change or instantaneous rate of change? At point A or point B? Where is the rate of change greater? Where is it increasing more? At A or B? At B, right? So the derivative is telling you about that. It's telling you how much it's increasing. So what's the rate of change at A? Well, if you want to know that, you just take the derivative and put in, all the derivative asks you for is the x coordinate. It doesn't ask you for the x and the y coordinate. You don't have to give both. You only have to give the x coordinate. So what is the x coordinate here? 1. So what's the value of the derivative there? 30. So what's the slope of the tangent line here? 30. So what's the instantaneous rate of change here? 30. Now, here we said it's going to be more or less than 30. More, right? Let's check it. Well, I have to give you another point. Let's say that was at 2. Okay, suppose that was 2. Then, by the way, what would the coordinates of this point be? 2 comma what? Here's the function. So 2 comma what? 2 times 2 times 2 is? 8 times 10 is 80, right? So the height is 80, not the instantaneous rate of change. The height of that point is 80, right? But that's not, okay. So, and also though, the instantaneous rate of change, we hope, should be greater than, if my sketch is correct, then the instantaneous rate of change at B should be greater than the instantaneous rate of change at A. And how do I check that? Well, I already checked what it was at A. And what was it? 30. So what is it at B? How do I check that? Again, the derivative tells you the instantaneous rate of change. And the derivative only needs, as input, the x-coordinate. So what is the x-coordinate we're talking about here? 2. So if we put that into here, what do we get? 120, which is certainly bigger than 30. So the instantaneous rate of change is bigger at B than at A. Now my sketch is probably not so accurate, but anyway, it does show at least that fact that it's bigger. Okay? So just before you forget, what the derivative is telling you, and just figure out, oh yeah, I can use this rule to do this, and I can do this rule and do that, and figure out all these derivatives, but you can't forget what it's for, when you're doing it. It's not just a game, right, to find the derivative, it has some meaning. Okay, it tells you the instantaneous rate of change of the function. Now, again, just to give that a little bit more meaning, if this is the total cost, suppose the total cost function, let me just use the same one, even though it doesn't really make any sense. But suppose the total cost function was this. I say it doesn't make sense because total cost isn't going to look like that. it's not gonna be an increasing, super increasing function. It's actually gonna be like something more like this, not really increasing that much. But just pretend. So suppose that was the total cost function. Now we find the derivative, which we can write as total cost prime. That's one of the notations for derivative. Or we have lots of different notations for the derivative. This is one notation, but this is using the prime as another one. So if we just said it was 30x squared, what does the derivative tell you if the function represents cost or total cost? It still means the slope of the tangent line, but that's not really very interesting. It has deeper meaning than that, or richer meaning than that. So what does it tell you? We talked about it. What does the derivative tell you? If you're talking about cost, and you take the derivative of cost, you get what? What is it called?
Marginal cost.
Marginal cost. So what does marginal cost mean? The cost of producing one more item. Right? So if I put in, suppose this 1 actually means 1,000. Okay, so suppose I put in 1, then what do I get? What number do I get here? I get 30. So that would tell me that the marginal cost of producing one more item if I'm producing 1,000, how much does it cost to produce 1,001? One more item. This would say it costs $30, for example. So the derivative tells you the marginal cost, and the marginal cost is the cost of producing another item. Now the reason I said this doesn't make sense is, this would say that the marginal cost of producing one more item when it's at, say, 1,000 is 30, and when it's at 2,000, it's more. It's like, what did we say, 120? But that doesn't make sense, right? Usually when you're talking about marginal cost, the marginal cost doesn't go up, it goes down. So that means that the slope should not be increasing like that. If this is a real cost function, it shouldn't be increasing like that, where the slope is low here and getting higher and higher. The slope should be more like this, like that. Now the slope is high here, which means the marginal cost is high there, but the slope is lower here, which means the marginal cost is lower there. That makes sense in terms of marginal costs. So that's why I said this function doesn't really make sense. But I just gave you an example anyway. But in our previous lecture, I did give you a function like this, and it did make more sense. Okay, so we have derivative. Now let's go back to just the math and forget about that marginal cost, and just remember these rules. So where are we? So we just did that top rule. How about an example of this one would be, suppose we ask for the derivative of x to the 4th plus x to the 6th. Okay, so what's the answer to that? Using the rule, so in other words, just doing it one step at a time, you would write the derivative and what goes in these two? Derivative of x to the 4th, and this one? X to the 6th. And they are what? This one is what? 4x to the 3rd. And this one is what? 6x to the 5th. So that would be the answer, using that rule. Okay, so we did that. Now this rule, I said, is not as simple as we would like it to be, right? And the answer is not this. It's not that. I said I wish it was that, but it's not. But and by the way, instead of using this notation, I'll use this notation. It's the same thing, just different notation. But it's not that, but it is. Does anybody remember what it is? What is it?
F prime G
F prime times G
plus
plus
G prime.
G prime times F. Okay? So that was the rule. And an example of that one would be the derivative of x cubed times x to the fourth. Okay? Now if we treated this function as f and this one as g, we don't have to treat it that way. We could just multiply the two of them together and then we don't need any rule like this. But if we wanted to, we could treat this one as f and this one times as g. And so what would we do? What would we do? F prime is what? 3x squared times g, x to the fourth, plus g prime, 4x to the third times f. So that would be the answer. Okay, which you could rewrite like this, right? This is what? 3x to the 6th, and this is what? 4x to the 6th. So 3x to the 6th times 4x to the 6th is 7x to the 6th. But like we said, you could have done it how? Instead, you could have just multiplied these two together, gotten x to the 7th, and then you'd still get the same answer, 7x to the 6th. But I didn't want to do it that way because I wanted to show you an example of this rule. Okay, and then this rule, I don't want to repeat this one. Well, I'll just do it. What was the rule? I think it was f prime g minus g prime f divided by g squared. But I'm not going to do that one. You can do that for homework. There's plenty of homework going on for that. Okay, and then we had one more. So I said that really we're asking for the derivatives of the different operations. What do I mean by the different operations? Plus, minus, times, and divide. Those are 4 different operations, right? And then I said there's one other operation that we can consider. And I asked you what it was, and nobody remembered, even though you're supposed to take fundamental math or know the contents of it. But yeah, but it was composition, right? Function composition. So what does that mean? Function composition is not written as f plus g. It's not written as f minus g. It's not written as f times g. It's not written as f divided by g. It's written usually as f circle g. And the meaning of it is what? Means that. Means don't add f and g. Don't subtract f and g. Don't divide f and g. Don't multiply f and g. This is not multiplying f and g. This is putting g into f. That's different than multiplying f and g. It doesn't mean the same thing. Okay? By the way, this is sometimes written like this. No. Yeah, like that. And usually the reason they write it like that is because if they didn't put the brackets around there, you'd get confused. So, like, this is the name of the function, f circle g, and it's applied to x. Like, usually we'd write, like, you know, k of x, right? And so we know that x is the variable, and k is the name, right, of the function. But if we didn't put parentheses around this, you know, it kind of looked confusing. It would look like, it just wouldn't be that clear. It would look like g of x and something f. It's not really clear. So they put the brackets around it to say that's the name and it's being applied to x. Okay? So that's why they write it like that. But the actual meaning is here. So what's an example of this? Oh, I didn't give you the rule yet. So what's the rule for the derivative of that? So it's not flat. Well, Or we can write it like that, or I can write it like this. Or, anyway, this is just another way of writing it, just to, whatever. Right, either way, but what's the rule? So you can write it like this, or like this, but what's the rule? So I just had it at the end of the last class, and the rule was this: f prime of g times g prime of x, like that. Okay, now let's do an example of this one. This one is maybe a little more interesting. So let's do an example of it. Suppose that f is equal to the square root of x, which can also be written like what? As a power. If I want to write x to the power of something, what would that be? X to the power of a half, right? Or 0.5. X to a power of a half, right? Okay, suppose that's f, and suppose this is g. X squared plus 8. Okay? Now, over here, I said, here, suppose that f is x cubed and g is x to the fourth, right? And then I said, what's the derivative of the product of them? Now, most people wouldn't bother using the product rule, this rule, to do it. They would just multiply these two together, and then that would give you x to the 7th, and then they would say, oh, it's 7x to the 6th, right? Most people would do it that way. But anyway, I gave you the expression here, and then afterwards I told you which one was f and which one was g, right? Right? But here, I'm telling you which one is f and which one is g first. And now let's get the expression first and then ask what's the derivative of that expression. So what do I mean by get the expression first? In other words, let's first write the question, what's the derivative of f of g? So what is f of g? So what is f? What is f? What's f? The square root of x. And what's g? X squared plus 8. So what is f of g? So what does that mean? That means I'm putting g into the square root function, right? Right? I'm putting g into the square root function, right? So what is that? Square root of x squared plus 8. Now, did I ask you the derivative question yet? No, we didn't get to that yet. I just said, here's a function. Okay, now I'm going to ask you the derivative question. And then you can use the derivative rule, the composition rule. Okay, so now I'm going to ask you, what's the derivative of this? Okay, so let me ask you that. What's the derivative of this? Okay, now, when I asked you, what was the derivative of x cubed plus x to the fourth, when I asked you that, you immediately saw which one was f and which one was g. Right? It's very quick to break it into two, right? It's like obvious, right? But if I ask you this one, what's the derivative of this? There are not that many people who are going to break it up into the composition of two simpler functions. So if I said, what's the derivative of this? I don't think many people are going to immediately break it up into a simpler f and g, such that this is the composition of that f and that g. Like here, when I asked you this, you could break it up in a second into the sum of two simpler functions, right? But here, if I ask you this, I don't even think anybody is going to see this as the composition of two simpler functions. Because we don't do that often, right? You don't practice that a lot. In fact, you don't practice it at all. Right? So you don't see this as the composition of two simpler functions, but you know that it is because I just constructed it as the composition of two simpler functions. So you can obviously see that it is the composition of two simpler functions. But if you just saw this, you wouldn't see it. Usually, most people wouldn't. Right? But it is the composition of two simpler functions. Which two simpler functions? This one and this one. In fact, that's how we just constructed it. Right? So I can say this is the composition of the usually I usually call it the outer function and the inner function. So what's the outer function here? The f function is the square root, and what's the inner function?
X squared.
The x squared plus 8. So it is the composition of these two functions, and if you can see it as the composition of these two functions, then you can use this rule, which is called the chain rule. You can use this rule. It says if you have the derivative of an outer function and an inner function, you can use this rule. But you have to first see it as the composition of an outer function and an inner function. You have to identify what's the outer function and what's the inner function, because this one says, because the rule says after you do that, find the derivative of the outer function, and this part, and then do something here, and then this part says find the derivative of the inner function. So if you can't even see it as the derivative of an outer and inner function, you're not going to be able to do this, right? But in this case, I hope you can see it as the derivative of an outer function and an inner function, because we just constructed it from an outer function example and the inner function example. So what is the outer function again? The square root function. And what is the inner function again? This one. So the rule is going to say, according to this rule, now what this says here is sometimes a little confusing. Read it like from the outside. So it says first find f prime, and then put g into that. So that's not so hard, not so confusing if you think about it like that. So it says first find f prime, and then put g into it. And then this part is very simple, just find the derivative of g. Okay, and then multiply the two together. So it's not that complicated actually. So let's do it. So I said that f is here, so I need to find f prime. So I think it's easier to write this as x to the minus 1/2. Okay? So that means I'll make space here. The derivative of f is what? If this is x to the 1/2, did I say minus 1/2? That's wrong. If this is x to the 1/2, what's the derivative of that? 1/2 x to the minus 1/2, right? 1/2 x to the minus 1/2. So that's the derivative of f, but we don't exactly just want the derivative of f, we have to put g into that. So I have to put g in for x. So okay, I'll do that. So the derivative of f of, that's not a good way to write that. Let me write it like this. So f prime of g of x. Right? So what do I get? So I have to put g here. So what is g again? X squared plus 8. G is x squared plus 8. So I have to put that in here for x. So I get 1/2. Instead of x, I have to put what again? X squared plus 8 to the negative 1/2 power. Okay, so that's this part. That's this part. So I'm almost finished, I just have to do that part. Right, so I have to take this times g prime. What's g prime? Let me write it here. So where's g again? g is here, x squared plus 8. And what's the derivative of that? 2x, right? So this is 2x. So I'm basically done. I needed this piece, which I already did over here. And I needed this piece, which is here. I just have to multiply those two together. Okay, so what do I get finally? Here. Put the answer here. What do we get? What is this piece? Where is it? It's here. It's here. So what is it? 1/2 x squared plus 8 to the negative 1/2. Okay, that's this piece. Now what's this piece? It's g prime. We have it somewhere around here. Here. 2x. That's the answer. Now this would not have been very easy to do without this rule. Now, as I said before, this would have been very easy to do without the product rule. You don't need the product rule really for this problem. But this, I don't think would be easy to do without this rule, without this composition rule, or the chain rule it's called. Okay? Now, how did we do this though? If I gave you this problem, how would you do it? Looks hard. Looks like there's no way to do it, no easy way to do it. Right? If you stare at this problem, what are you going to do? What do you have to, what's the luck here? What's the lucky thing to see here? The lucky thing to see here would be if you were lucky enough to see this as the composition of two simpler functions. If you could see it as the composition of two simpler functions, then you could say, oh, I can use the chain rule. It's called the chain rule. So you'd say, I could use the chain rule, and then you could do it, like we just did it. But if you don't see it that way, you won't be able to use the chain rule. How about this problem? Suppose I gave you this one. The derivative suppose I give you that problem. Now you could multiply this out 15 times and you'll get a very long polynomial. And then you could do it. You could do it that way, but that would probably take a really long time. Right? But there's another way to do it. But you have to be able to see it not as the sum of simpler functions, not as the product of simpler functions, but as the composition of two simpler functions. Now, as I said, we're not trained to do that. We don't learn to do that, right? It's like, remember when you were in third grade, and you had to learn things like this. Write 24 as the sum of two numbers. Well, that was probably in second grade that you did that. Write 24 as the sum of two numbers, and what would you say? 10 and 14, right? Or 12 and 12, or whatever, right? 20 and 4, right? So you learned how to do that, right? You learned how to, at first it wasn't so easy, right? And then maybe the next year they asked you, write this as the product of two numbers, right? And then you'd say, oh, 8 times 3, or 2 times 12, or whatever, 6 times 4, right? So you were able to break it up into the product of two simpler numbers. Well now, we're saying take a function like this, and can you break it up not as the product of two simpler functions or the sum of two simpler functions, but as the composition of two simpler functions? And we already did it here. Now, can you do that here as well? Can you break this up as the composition of two simpler functions? So what might it be? So what we're asking for is what's the outside function and what's the inside function? So what's the outside function here? X to the 15th. And what's the inside function? X to the 4th plus 7x cubed plus 7, right? And then you have it as the composition of, let's say the outside function is x to the 15th, and the inside function is x to the 4th plus 7x cubed plus 7. So then this is equal to the derivative of what? Of what? F of g of x. Right? And then you can use it, now you see, oh, well this is a chain rule question, because it's the derivative of composition. So that means you can use this rule. And then you just have to find the derivative of the outside function. So that's the derivative of this, which is easy, 15x to the 14th. You have to put in g into that, but that's not too hard. And then you have to find g prime, which is also not very hard. Okay? So what's this rule called again? The chain rule. Okay? The chain rule. And what does it solve? The derivative of a composition. Right? So now how many rules have we had? Well, we have 1, 2, 3, 4, 5, and the chain rule 6. Okay? Now again, I'll just remind you again. Why do we do the derivative? This is just how to get derivatives of certain kinds of functions. But what good is the derivative in general? I erased it, the picture, but it tells you the instantaneous rate of change. And like in the example of cost functions, that means the marginal cost. Okay? Any questions about this? Any questions about this? Okay, so we did that. Okay. So here we have, okay, now let's go to this one. So we covered actually all of this homework. Marginal cost and product and quotient rules. I don't know what happened to the other rule. But anyway, okay, let's go to this one. Big assignment on derivatives of logs and exponents. Can everyone see that? Big assignment, I think it's 29 problems. Okay, so I wanted to warn you, so I called it big assignment. And also I gave you 1 extra day to do it. So instead of 6 days, you have 7 days from whatever, but actually you have a lot of time to do it now. But, well, no, you don't have a lot of time to do it. Anyway, you have, it's due on the 30th. So it's 1 extra day, more than usual. Okay, but still, you still have a lot of work to do. All right, let's take a look at this though. Let's take a look at this one. And in this one, you're going to use these rules. That's why I made it big, because it's good exercise for using these rules. Okay, now we need to learn two things though first. And that is, I'm going to just tell you, tell me about this function. And tell me about this function. Oh, and then we have to do a little bit more than that, actually. Oh, I forgot about that. Okay, anyway. Do you know these functions? I think we covered them already, right? So what does this one look like? F.
Exponential.
Looks like this. Right? It grows quickly. Goes through 1. That's F. Right? And how about G? What does that look like? That looks like this. Grows very slowly. This is also 1 here. Okay, and what's the relationship between these two? Is there any relationship? Like, how about pictorially or graphically? Is there any relationship between these two? Huh? He said, what's that mean?
To X line there.
What's that mean? He's right. This. What does that mean? Huh? Yeah, the inverse, right. But what about graphically? He meant this, right? He meant that if you draw this line, this is a 45-degree angle. If you draw that line and you rotate this or reflect this through that line, you'll get this graph, which is the log graph. So these have that relationship, that if you rotate through this line, this one could be that one, or this one, that one. They have that relationship. And when graphs have that relationship, it turns out that they are inverses of each other. Now, what does it mean to be the inverse? I know, were you supposed to go through that in math, fundamental math, but what it means is, can somebody tell me another example of two functions that are inverses of each other? How about these two? Those are also inverses of each other. Let's just check in terms of the graph. What does the graph look like? What does x squared look like? Like that. What does the square root of x look like? Like that. And same thing. If you rotate through that line, one becomes the other. Okay? So those two are inverses. But these two are more suggestive about what inverse means. What's the relationship between these two? Can anybody come up with an interesting statement about these two? Maybe you wouldn't come up with it about these two, even though these are also inverses, but these two you might come up with an interesting statement about the two of them. What statement is that? Well, if I do this and then do this, what do I get back? Let's say put 5 in here. I put 5 in here, I get what? 25, and then I put that in here, what do I get? 5. So in other words, if I do this and then do this, what happens? It's like doing nothing at all, right? Right? That's what we mean by two functions are inverses of each other. If you apply one and then apply the other, you just get the original x back again. Right? But how do I write that if I do one and then do the other? How do I write that? What's the symbolic notation for doing one and then doing the other? Suppose f and g.
Domain.
Now, if I do, let's suppose I do g first, or let's suppose I do f first and then g. How do I express that? That means I do f first and put that into g, right? Right? That's what I just said. Do f first and put the result into g, right? How do I write that? I write it like that, right? Does that mean first do f and then put that into g, right? And that is equal to what? Doing nothing. That's equal to x, right? So what do we mean by two functions are inverses of each other? This. It means that if you do one and then do the other, you get just x back again. That's what inverse means. Two functions. Just like, what does it mean to say that 5 and negative 5s are inverses? If you, no, I don't want to go through that, but that's the same concept. But anyway, okay, so it's the same concept as 5 and negative 5s are inverses, or 1/5 and 5. are also inverses, right? 1/5 and 5, you multiply them together, you get 1, you add them together, you get 0. The kind of same idea here. But anyway, so two functions are inverses if you do this and you get x back again. Okay, now I didn't go into it in detail because you're supposed to do that in fundamental math, so I'm not going to go through all of it. Okay, anyway, these two functions are also inverses. So what does it mean? So what? They're inverses, so if I put one into the other, I'm supposed to get what back?
X.
X. So how do I put one, like suppose, so f of g equals x, and also g of f equals x. So how do I write that for this particular f and g? What's f of g mean? Means put g into f, right? So what does that mean? Put g into f. That means
Yeah.
e to the ln of x, right? I put, here's, did I do that right or wrong? Yeah. I put g for x, so instead of e to the x, I get e to the ln of x. So that's equal to what? X. And this? How do I write that? G is what? G is what?
ln.
Ln of x, so I'm putting what into that?
E.
F, so it's ln of e to the x. It's also x. Because they're inverses. Okay, they are inverses, so this has to be true. Okay? They are inverses, so it has to be true. So it's not like exactly a mystery. It's just because they're inverses. Just as if you do one and then the other, you get x back again. Okay? All right, so we just talked about these two functions, ln of x and e to the x. Right? Now, why are we talking about them? Well, one reason is because they come up a lot. Like, when does e to the x come up? Does it ever come up? Yeah, we talked about it for compound interest. We said that e to the x comes up if you do continuous compounding. So it actually comes up in business. E to the x actually comes up in business, so we have some reason to talk about it. Now, what are we doing in this lecture? Are we talking about compound interest? Not really. What have I been talking about for the last minutes? Derivatives of different functions, right? So, we would like to also be able to talk about derivatives for these two functions. Okay? So, I'd like to know which one is f. F is e to the x. I'd like to know if f equals e to the x, what is f prime? Okay? Now, you don't have any way to do that. Okay? And if g equals ln of x, what is g prime? And again, you don't have any way of doing that. So all these rules, we don't go into where they came from in our class. You can read it. It's not that hard to follow it, the rules, or to see how they're derived. But we don't have that much time because we're trying to cover a lot in a very short time. I can't sit around and do that. So, but it's not that hard to get any of these rules. Like, where did this rule come from? It's not just God didn't give it to me. It had to be proved from somewhere, right? So, same with this and all of them, right? Maybe God did give it to us, but not directly. But anyway, so it has to be proved. but it's not that hard to prove them, but as I said, we don't have time. So the same way, it's not that hard to figure out what the derivative of this is. And it's not that hard to figure out the derivative of this either. Now let me, except that I have to remember this one exactly right. It's, ln of x is only defined for positive values of x. That's 1 over t, 1 over x. Okay. Okay, let's say. Anyway, actually we can figure this one out. Actually, I think I can figure, I forget this thing, I'm embarrassed to say, but I forget if I know this exactly or not. But actually, if I can tell you this, I should be able to figure this one out. So let's try and prove this one after knowing this one. So just to show you one proof, because I'm not sure I remember the right answer, which is really embarrassing. But anyway, so what is it? E to the x, the derivative is?
E to the x.
They say it's the easiest one to remember.
So?
The derivative of e to the x is e to the x itself. So if f is equal to e to the x, the derivative is also e to the x. That's pretty weird, but that's the only function whose derivative is the same as the function itself. There's never any other function that will do this. Okay, the derivative of the function is the same as the function itself. Okay, so we have to, that's just a fact. Now let's see if I can prove or get the answer for the other one. So, that's right. First of all, let's write that the derivative of e to the x is what? E to the x. Okay, let's just write that as a fact. Now, let's do the derivative of, I want to do it this way, I think. Of e to the ln of x. The derivative of e to the ln of x.
1.
So, on one hand, e to the ln of x is what?
X.
Remember? E to the ln of x is, they're inverse functions, so e to the ln of x is x. So on the one hand, this is asking me for the derivative of x, which is super easy. It's just 1, right? Okay. Now, on the other hand, I can view this as the composition of an outside function and an inside function. Right? What's the outside function? E. E to the something. And what's the inside function? ln of x, right? So what? So the chain rule tells me how to do this then. Right? The chain rule. So what does it say? The chain rule says that you take the derivative of the outside function, evaluate it as the inside function, that's what they say. That one times this one. That's what the chain rule says. Now which one is f? F is e to the x, and g is ln of x. Now, I hope I did this right. Yeah, I did. Okay? Everyone see so far what I've said? Or not? No? Okay, let's say it again. I'm trying to remember what the derivative of ln of x is, and I think I know what it is, but I want to prove it here. So I'm going to prove it. So I remember how to do it. I remember how to prove it, even though I don't quite remember the answer. So, so here's how I'm going to figure it out. So I decided to write this here, e to the ln of x. Now you'd say, well, why did you write that? Because I remember this is how it goes. Okay, so e to the ln of x, and I'm going to ask for the derivative of that. Okay, now, but on the one hand, e to the ln of x is what? It's just x, right? Because they're inverses, right? So I'm just asking for the derivative of x, which is simple, right? What's the derivative of x? It's just 1, right? Derivative of x is just 1, so that's easy. But, on the other hand, I can express this, I can think of this as something that I need to apply the chain rule to. I have an outside function and an inside function. What's the outside function? E, and what's the inside function? ln. So, the outside function is e, and the inside function is ln, right? And the chain rule says what? That it's going to be the derivative of the outside function, and then you put the inside function into that derivative, times the derivative of the inside function. So let's try it that way and see what we get. So what is the derivative of the outside function? Well, the outside function is e to the x, and I already told you it's the only function whose derivative is the same as the function itself. So the derivative is e to the x. So it's e to the x, but I'm not putting x in, I'm putting g in. So it's e to the ln of x, again. Right? Did I do that right? I think so. That's right? Times what? G prime. But what is g? ln of x. Well, that's the one I don't know. I can't remember. But I'll just write it as ln of x. I'll just use that for the notation for the derivative, or you can write d of x, whatever you want to write, I don't care. Okay? So, but look, I found the answer. Because what am I really trying to find here? What couldn't I remember? I couldn't remember the derivative of ln of x. Well, I have an expression now for the derivative of ln of x. What is it? It's this times this equals 1. Right? Right? That times that equals 1. So what can I say? I can say the derivative of ln of x is equal to what? 1 over this, right? E to the ln of x. But what is e to the ln of x? Those are inverses, right? So e to the ln of x is what? Just x. So finally, the derivative of ln of x is what? 1 over x. So that was the answer. That's what I knew it was that, but I was pretending I didn't know. Okay? So it was 1 over x. Okay? But you can see how you can prove it. If you know the derivative of e to the x, that implies that the derivative of ln of x has to be 1 over x. Okay? So now we have these two facts at our disposal. So what here? Let's write them down over here. If f of x is e to the x, the derivative is what? E to the x. You have to remember that. And one more fact. You can either remember it or you can prove it using the chain rule. What is the fact though? If g is ln of x, the derivative of that, g prime, is what? 1 over x. Okay, so the derivative of ln of x is 1 over x. Okay, so now we have these facts. Okay, everyone? You have to remember those facts. Okay, so you have to, just like kanji, you have to remember certain kanji. Actually, you have to remember a lot of kanji. These are not so hard to remember. But you need at least the derivative of e to the x is equal to e to the x. Okay, any question? Okay, now let's do some of the homework here. So let's try the first one. So, okay, why don't you all try to do it yourself first and see what you get. So this one here. Find the derivative of ln of x plus 8. And I'll give you the clue, the hint. What rule? What's the rule? The chain rule. Well, actually, that one is not so clear. But No, okay, yeah. Okay, that one. So, I'll give you the hint that you use the chain rule, and I'll give you one more hint. If you need the chain rule, you have to see it as the composition of an inside function and an outside function. So you can call the outside function f and the inside function g. You have to see it as the composition of an outside function and an inside function, and then you can use this chain rule if you can read it here. Here, f prime g of g times g prime. So try and do it yourself, see if you can see what you get. You need to practice it. Write it down. Write it on a piece of paper. Good practice. At least try it. If you don't try it, then when I tell you the answer, you won't really get it. I don't know if you can read the board. 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 So here's the chain rule here. So also written somewhere else. No, I don't even know what that's it. Okay, can we do it? Can we try now? Everyone get an answer? Okay, what's the outside function in this problem? What is it? ln of x, right? And what's the inside function? What? X plus 8. So f, they called f the whole thing, but in this notation here, f is ln, right? And you know, they called the whole thing f, but we don't want to do, I want to use this here, so I have to call, the outside is f, so that's ln, and the inside is what? X plus 8. So, what do we have to do? Take the derivative of the outside, which was, we just said was ln, so the derivative of ln is what? 1 over, okay, and then, but it's not 1 over x, it's 1 over g, because we're putting g in, right? It's not 1 over x, we're putting g in. It's 1 over g, which is 1 over x plus 8. So let's write that down. 1 over x plus 8. That's this part. Now we need this part, g prime. So what did we say g was? X plus 8, so the derivative of that is just 1. So it's just this times 1. So it's just 1 over x plus 8. Okay? Any question about that? Okay, good. Anybody have any questions? Okay, so, good. How about this one? How about this one? Okay, so try this one now. Exercise, another exercise. So, the function is e to the x plus 3.
The answer is the same.
E to the x plus 3, and you're supposed to find the derivative of that.
The same.
It's going to be simple, but just do it anyway. Do it methodically, step by step. The answer is going to be kind of boring, but do it step by step anyway. At least you're getting your homework out of the way. Right? Because these are the homework problems. So all of these are going to be chain rule problems. They're all chain rule problems, or probably most of them are. So that means you have to see there's an outside function and an inside function. So what is the outside function here? E to the something, right? And what is the inside function? X plus 3. So, what's the derivative of e? E to the something. It's e to the something, right? And what are we putting in? The something. So what do we get for this term? The exact same thing, e to the x plus 3. Right? I think, isn't that right? Yeah, that's right. And then, what's this term? The derivative of x plus 3, which is what? 1. So what do we get? E to the x plus 3. I think that's the answer, right? We're going to agree with that? Yeah. Okay, good. How about... Okay, this one is not the chain rule. This is not the chain rule. So not all of them are chain rule. Let's take a look at this for a minute. Let's see what they say here. Derivatives of logarithmic and exponential functions. What's this rule say? The derivative of ln of x. This is another way of writing the derivative. is equal to
1 over.
1 over x. So that's what we've been saying. And they also remind us that ln of x is equal to what? Can you read that or not? Can you read it now? ln of x means what? The log base e of x, right? That's what we mean by ln of x, right? Okay, how about this one? How do they do this one? Can you read this? Look at this one. What rule do we have to use here? We don't use the chain rule here. What rule? How many functions can you identify here? Here's one. What's it called? ln of x. And where's another one? X. X is also a function. So what are we doing with these two functions? Are we adding them?
Plus.
Are we dividing them? No, we're doing what? We're multiplying them, right? Right? X times ln of x. That's what this means. Maybe you're not comfortable with that notation, but that's what it means. X times ln of x. That's what it means. So if that's what it means, then what rule do we need? The product rule. What was the product rule? Do we have it here? Yeah, but we erased it. But here it is. F prime times G plus G prime times F. Okay? So, which one, this one is F, and this one is G. X is F, and ln of x is G. So what's the rule? F prime of this, so what's the derivative of x? 1 times G times ln of x plus just x without taking the derivative times the derivative of this one, 1 over x. So what do we get? This plus that, we get that. Okay, that's the answer. Any questions about that? That was not the chain rule. But this section is about logs, so it doesn't have to be about the chain rule. It just has to be about logs or exponential functions. Here's another rule that I didn't do. This is another one you have to remember. Let's repeat it. Let's all say it together. Okay, let's read it. This means what? This symbol means what? The derivative. How do we read this part here? Log base b of x. Okay? So everybody say, read this together. The derivative of the log base b of x is equal to 1 over x ln of b. Okay? Did everyone say that? Okay? So you have to remember that one. Or you can prove it if you want. Let's read it one more time. Ready? One more time? How do you read this? Derivative of log base b x equals, right? Okay, can you read that? Can you say it? Can you remember it? All right? Okay, now, is this really correct? Oh, well, I hope so. But how about if b is equal to e? How about if b is equal to e? Because this b can be anything, right? Any base. Not
Positive number.
any positive number, yeah. So it can be e. So how does this rule read if b is equal to e? Let's read it. log base e of x, but another way of writing that is what? ln of x, right? Right, if I put e here, then another way of writing that is what? ln of x. So then we're asking for the derivative of ln of x, which is what? We already know the answer to that, it's what?
1 over.
1 over x. So is this actually equal to 1 over x? When b is e. ln of e is 1. How do you know that? I don't want to spend time on it. It's kind of simple. It's kind of very simple, but I don't want to do it right now. But anyway, ln of e is 1, so this does give you 1 over x. Because you can, it's easy to think about it. It's just say, what do you have to raise e to get e? Right? That's how you deal with logs, right? What number do you have to raise this to get that, right? That's what log means. So what number do you have to raise e to get e? 1, of course. So that's ln of e is 1. So I just get 1 over x. So anyway, okay? So this is a generalization of the other rule. This is more general than the ln rule, right? The log of ln is less general than this. Because this, when b is equal to e, gives you the log of ln, the derivative of ln answer. Right? So this is more general than the derivative formula for the log for ln of x. Right? Everyone agree with that? If e is equal to x, I'm sorry, if e is equal to b, then this becomes the simpler rule, but this applies not just for b equal to e, but for b equal to many different things. Okay? Alright, so we have that rule. So let's try and remember this. What's the rule again? 1 over x ln b. Okay? I have to somehow remember that. 1 over x ln b. Okay, that's for log base b of x. Okay. So if we remember that, then let's go back to this one. What was that rule again? I'll give it to you again. Maybe you want to write it down. Here it is. Log base b of x, 1 over x ln b. Okay, I'll let you write that down and then try and do the other problem. Log base b of x, 1 over x ln b. Okay, everybody record that? Okay, now try and do this one. So this one also, you don't need the chain rule. You just need that formula that you just noted. What's the answer? This is log base 2 of x. So the answer is what? 1 over x ln of 2. Okay? Everybody okay with that? Okay, so that's what they want you to put in there. Okay, let's go to some other ones. We don't have time to do them all, but, oh, sorry, we need something else here. Oh, actually, they derived that one. In fact, they derived both of them. So if you want to read the proofs, they are here. Next one. Okay, now maybe you get confused about this, but here's a quick example which makes it maybe clear, because this looks confusing. But let me show you by the example, then you'll understand this generalized rule. First of all, can you read this? Is this readable? Big enough to read or not? Make it bigger? Make it a little bigger. Okay, so what, here we're asking, here, which rule are we going to need? We have an outside function and an inside function, right? What's the outside function here? ln, and what's the inside function? X squared plus 1. So we're going to have to take the derivative of the outside function, the derivative of ln, but that's equal to what? 1 over, but what are we putting into it? X squared plus 1, so it's 1 over x squared plus 1 times the derivative of the inside function. This is the inside function, the derivative of that is written like this, right? Okay? So the answer is 1 over the inside function times this, right? So it's this times 2x, right? Okay? Now, here's how they write it here. Let's look at it, because you'll see it written like this, and then you'll say, what does that mean? But look at it, it's exactly this problem. This says, look at this. Please look at this, because if you don't get it, it looks complicated, but if you do get it, it's easy. This and this are basically the same kind of thing. So what do you see here compared to here? Let's compare this part and this part. What do you see? Well, I see a d over dx here and a d over dx here, right? So that means the derivative. I see the derivative question here and the derivative question here. Then I see the ln and I see the ln. And then this is u and this is x squared plus 1. Okay? Now what they mean by this u is they mean some function of x, any function of x, right? Here's a function of x. So that's what they mean, they just mean some function of x. So what's the rule for doing this? It's 1 over that function of x, right? So that's what they write, 1 over that function of x times what? The derivative of that function of x, right? Which is written as du dx, right? That's we wrote d of this thing dx, right? So instead of writing d of this thing dx, d of this thing dx, if we're being general, instead of specifically x squared plus 1, we just want to talk about some function of x. We say not d of x squared plus 1, but d of u, where u is any function of x. Does that make sense? So this is an expression of the chain rule specifically for ln of some function of x. So u is some function of x. Okay? Does that make sense? All right? And this is just a specific example of it. So this is not exactly the chain rule because this is not completely general. This is just for the ln rule. It's the chain rule applied to ln only, right? But the chain rule is more general than this. Okay? And this is also the same kind of thing if we have a function of, if we're trying to do the derivative of the log of some other function, then what's the rule? It's the derivative of the log base b of that u, which is what? 1 over that u, ln of b, times the derivative of the inside function. What's the name of the inside function here? U. The name of the inside function is u, so it's times the derivative of u. Now the way you read this, with this notation, okay, everybody read this together, please, at least once. I want you to say it at least once, so at least you can say you've read it once. Read just this here. The way you read it is du, the way I read it is du dx. Du dx. Okay? Whereas normally we write dy dx, right? Okay? So this is like, this is like u is also a function of x. Right? U is also a function of x. Okay. Okay, so let's do this one. Let's do this one. No, I don't want to do that. We've done enough of those. We've done them. You can do them. Let's see what else I have here. Okay, these are all the same. So you can do all of these. There's only one problem here. Let's see. Sorry. All right, let's take one more look at this here, part C. So look at this. What's the question here? Can you read it? Because this comes up a lot in the homework, a lot. Or I tried not to give you too many of these, but I couldn't avoid a few. So let's look at this one, part C. Before we start, so what is the question here? The derivative of ln of the absolute value of x. Before we start, note that ln of x is defined only for positive values of x. Now, if you remember my picture of ln of x, here's the picture of ln of x. It only is defined for positive values of x. There's no value, no graph to the left of the y-axis. So it's only defined for positive values of x. So its domain is the set of positive real numbers. The domain of ln of absolute value of x, on the other hand, is what? What about the domain of the absolute value of x? Well then, you're allowed to put in negative values. Why not? Why? Because even if you put in negative values for x, when you take the absolute value, that's okay, right? Because it's still positive, right? So this function, the domain is not just the positive numbers. It's the positive and the negative numbers, but not zero. Right? Everyone agree with that? So the domain of ln of x, on the other hand, is the set of all non-zero real numbers. For example, the ln of absolute value of negative 2 is just ln of 2. For this reason, ln of the absolute value often turns out to be more useful than the ordinary logarithm, because it's defined more places than the ordinary logarithm. Okay, so how do we talk about the derivative of ln of the absolute value of x? So how do we do that? What rule are they using here? What? Two rules, but the one that I'm thinking about, there's two being used, but which one do you think I'm asking about? The chain rule. Of course, they're also using the derivative of ln of x, but they're using the chain rule. So what do I mean by they're using the chain rule? What's the outside function? ln. What's the inside function? Absolute value of x, right? What does the absolute value function look like? It's a v. Like this. Right? This way and this way. It's a v. Right? You know what I'm talking about? So what's the derivative? It looks like this, right? So what's the derivative? The absolute value function looks like this. Right? So what's the derivative when on the positive side? When x is greater than 0, what's the derivative?
1.
1. The slope of that line is 1. And what's the slope on the left side? Negative 1. So the derivative there is negative 1. Okay? All right, so if you want to write the derivative, which this will really confuse you, what's the derivative? We didn't draw any of these pictures, so I'm not sure it's a good idea to start right now. But what's the derivative to the right of 0? What's the derivative to the right of 0? It's 1. So they write this. This is such a horrible picture to look at. But they write that. This represents the derivative. This means, this is not f, this is f prime. This means the derivative is always 1, the derivative is always negative 1. Anyway, maybe that's just needlessly confusing. So, let's look here. So, this is the chain rule. So the derivative of ln is what? Is 1 over whatever's inside. So that's 1 over the absolute value of x times the derivative of the absolute value function. But the derivative of the absolute value function can be written like this. This is going to be 1 and negative 1 in the right places, if you think about it. So like when x is positive, what is this? It's x over x, which is 1. And when x is negative, what is this? It's positive over negative of the same magnitude, so that's negative 1. So it could be written like this. So you get this over this, finally you get this. So what's the derivative of this? 1 over x. Okay? And you're going to need that fact in various problems. Okay? So have fun with all the homework. Okay, and then next week you'll get another big assignment. And the week after that. Because I want to cover everything.